Hello everyone, we are Team 6 and we are going to present our understanding on the paper Improving 2D Feature Representations by 3D-aware Fine-Tuning, which was accepted in European Conference on Computer Vision, ECCV 2024. This video is a part of our term presentation for our coursework on CS 671 Deep Learning and its application at IIT Multi. So let's start with an overview on how the flow for the presentation is going to be. So we are going to talk about introduction to the paper, abstract idea, related work, objectives, methodology, result, conclusion, and reference. So let's get started with the introduction of this paper. And what is the problem trying to solve? The main crux of this paper is how integrating 3D understanding into 2D models can enhance their performance in various computer vision tasks. So let's start by understanding the core motivation. So traditional 2D visual foundation models like Dino V2, Clip, or MAE are powerful, no doubt, but they look at the world purely through a 2D lens. They don't truly understand 3D structure. So when these models see images, they focus on textures, colors, and shapes in flat space, but completely ignore how things are arranged in depth. Imagine looking at a photograph of a room. You see a chair in front of a table, a lamp in the corner. To us, these 3D layouts is obvious, but to a 2D model, it's just pixels. There's no understanding that one object is behind another, or that is closer or farther away. That's the problem, especially for tasks that demand on spatial reasoning, like depth estimation or semantic segmentation. This is where the paper steps in. It proposes a method to give these 2D model kind of 3D awareness without making them full 3D models. It lifts 2D features into 3D space, fine tunes the model based on this representation, and then applies it back to regular 2D tasks. This small tweak results in big performance gains. So, what's the problem? Well, when you train on a unstructured 2D images, you implicitly discard all the geometry. Like you don't see what is there in the image. You just focus on finding patterns. You lose multi-view consistency. Like you don't give a damn about is if there is a sofa, is there a table in the image. You just try to find some edges, patterns, complex patterns. The network might recognize a chair from one angle and another chair from different angle as two entirely different objects. We basically throw away the 3D context when we fixate on 2D projection. Why is that a big deal? Because many downstream tasks like semantic segmentation, depth estimation, object detection would benefit from richer understanding of shape and space. Without any 3D awareness, models struggle in scenes with complex occlusions or unusual viewpoints. You might find a model trained on one indoor dataset bombs when you saw it to a new environment or a slightly different camera angle. That lack of generalization exactly what we are trying to overcome. The paper proposes two-stage framework to solve this problem. So, I will give a high-level approach of this paper. So, stage one is lift 2D features in 3D using a Gaussian splatting. Think of this as that uh, those flat features learned by a foundational model like Dino V2 and inflating them in a 3D cloud of Gaussians. Each Gaussian encodes not just a color or textures, but also spatial location in 3 dimensions. This exploits multi-view consistency. Like you can see a image, particular image, from different viewpoints. So it would allow us to grab features from different views of the same object alignment and complement each other. And the stage two talks about using the 3D aware feature to fine tune the original 2D model. Once we have this 3D representation, we can render features back to any viewpoint. This rendered features becomes a new form of training data that carries implicit 3D knowledge. We then fine tune the original 2D model so that it internalizes those knowledge. In essence, we distill 3D awareness into a model that still operates on a 2D images. More details of these would be discussed in a while. So there's an abstract. So traditional 2D visual foundation models lack understanding of 3D structures, as I mentioned before. And this paper introduces a method that lifts 2D features into a 3D Gaussian representation. So let's break down. So we'll break down this abstract and the process using the given feature. The problem with the 2D foundational models, most models are trained on a static 2D images and lack any sense of real world geometry. This limits their understanding, especially when trying to generalize to a new environment or complex scenes. This paper tackles this head on by introducing 3D aware fine tuning. Lifting 2D features into a 3D Gaussian representation. This is the first key step. We start with 2D features, say from Dino V2, then lift them into a 3D space using something called 3D Gaussian splitting. What's happening here is that each feature from 2D image becomes a small 3D Gaussian blob, like a point in 3D Gaussian, placed into a volumetric space using multi-view consistency. This way, the model constructs a 3D understanding from multiple 2D views. So this is how the original image is and how the 3D features would look like. 3D features would look like. Next, so the paper proposes a 3D aware features fine tuning. So in this step, we fine tune the original 2D model using 3D aware features. These features now rendered from the 3D Gaussian volume serve as a technical signal. The 2D model learns to produce features that match the 3D rendered ones. So even though the model operates on 2D images, it learns to embed 3D semantics in its feature map. Refer to C and D image. I hope that's visible to you. This is where we are talking about C and D, right? You can clearly see the improved structure and object boundaries in D. Like you can see that there is a sofa and it is trying to understand there is a sofa, there is a couch, there is a chair. So it is getting better. So why it works? Like how, why does this works when we use it for our semantic segmentation and other work? Once the model is fine tuned in this way, it performs better on a downstream task like semantic segmentation and others. These tasks need a sense of 3D space, so adding this awareness helps a lot. On the right side of a figure, you can see the results. So this technique is especially useful in unseen domains, places where the model hasn't trained directly. The 3D aware fine-tuned models still perform well there, which shows that they have learned a deeper and more transferable understanding. So, to understand the novelty of this paper, let's explore some of the key related work. The first one is 2D representation learning. Traditional models like Dino are trained purely on 2D images using techniques such as contrastive learning or masked image modeling. While effective, they completely lack any spatial or depth awareness. They treat the images as flat, so they don't capture how the images are positioned relative to each other in 3D. The second one is feature fusion fields. These works aim to convert 2D features into 3D using a method like NERF, that is neural radiance fields, which is great for reconstructing scenes. But the main limitation is that these approaches usually stop at creating 3D models. They don't bring that 3D knowledge back into they don't get back that 3D knowledge back into 2D models. So the 2D foundation models don't benefit directly. The third related work is injecting 3D priors into 2D models. Other attempts have tried injecting 3D signals into 2D models using some geometric constraints or uh, surface normals or mass modeling. But these approaches often require heavy pre-training or additional modules that add complexity and does not always translates to performance improvement. So this paper stands out by being simple yet effective. It lifts 2D features into 3D using lightweight Gaussian splitting and uses that to fine tune the 2D model and delivers very strong performance. So, what our objective is, like we want to inject 3D awareness efficiently. The goal is to enrich 2D models with 3D understanding without redesigning architectures or retraining from scratch. That's why this approach uses existing backbones and just fine tunes them. Second is improving our performance on spatial tasks like semantic segmentation and depth estimation. So the objective is to enhance both of them using 3D aware signals. Ensure scalability and transferability. The method should work across different tasks, models, and domains without needing a different type for each setup. It should be memory efficient and should be scalable to real world use. So let's figure. It shows how 3D aware fine tuning enhances the feature across various 2D vision models. Like you can see in this Dino V2, V2 reg, clip, ME, and D3. They're not able to capture a lot of information. Like they are not able to capture, they are just dividing this into segments. You can see, have a look on Dino V2 reg. And about clip, it is not able to understand that there is different things over here, and ME performs really horrible. So once when we fine tune, we can see that the results are much better than before. So post fine tuning, features become sharper, more structured, and better aligned with the object boundaries. This clearly demonstrates that injecting 3D understanding significantly improves spatial awareness. Importantly, these gains come without changing the model architecture. So moving on.
Let us begin by understanding the high-level methodology proposed in this work. The major framework is structured into two major stages, each addressing a key limitation of conventional 2D vision models. Stage 1 focuses on lifting 2D features into 3D representations. This is achieved by applying 3D Gaussian splitting, a differentiable rendering technique that distributes learned feature vectors across a continuous 3D volume represented as Gaussians. The aim is to produce multi-view consistent features, meaning features that are spatially and semantically coherent across different camera views of the same scene. The approach begins with a pre-trained 2D backbone, such as DynoV2, which extracts features from each image in a multi-view sequence. These features are then embedded into a sparse set of 3D Gaussians. Each Gaussian stores a low-dimensional latent vector, along with geometric properties like position, scale, and opacity. A small CNN decoder is later used to project these latent vectors to recover the original high-dimensional feature space, effectively enabling the model to hallucinate full 2D features from a minimal 3D representation. Stage 2 is where the model learns to generalize this 3D knowledge back to 2D. Specifically, the original 2D backbone is fine-tuned using synthetic image rendered from the 3D Gaussians. During this stage, the rendered images, now enriched with 3D aware features, are used as supervisory signals. Crucially, this fine-tuning process is lightweight and computationally efficient. The model is trained with small batch sizes for just a single epoch, yet it shows significant gains across downstream tasks like semantic segmentation and depth estimation. Together, these stages form a loop. 2D features are lifted into a compact 3D form, and then the improved 3D representations are fed back to enhance the 2D model. Now, let's delve deeper into the training pipeline, which visually summarizes the full process of creating a 3D aware 2D model. We begin at the top left with a set of multi-view RGB images of an indoor scene. These images are passed through a 2D feature extractor, typically a frozen pre-trained vision transformer like DynoV2 or MAE. The output here is a per pixel embedding for each view. This is the input to our stage 1 process, where we employ 3D Gaussian splitting. In this step, we optimize the positions, opacities, and feature embeddings of a sparse set of 3D Gaussians, so that when these Gaussians are rendered into any camera view, the resulting 2D projection maintains semantic and geometric consistency. The output of this stage is what we call 3D aware features. These are feature maps that encode full encode not just local appearance but also 3D scene structures. Thanks to their integration over multiple viewpoints. Now we enter stage 2. We randomly render these 3D Gaussians into novel views. The resulting rendered images contain synthetic 2D feature maps that are spatially coherent and contextually enriched. These rendered feature maps are then used as a supervised signal to fine-tune the original 2D backbone. During this during this process, a loss function, usually L1 loss, or L2 loss, but L1 loss is still preferred, is computed between the predicted features from the 2D network and the rendered features from the 3D Gaussian model. By optimizing this loss, we effectively distill 3D scene knowledge back into the 2D model. This makes the 2D backbone more view consistent and better equipped to handle 3D tasks, even when given only single view inputs during inference. This slide represents a more granular and visual representation of both stages, reinforcing the intuition behind each process. Let's first focus on the left hand panel, the stage 1 lifting features to 3D. Here, we process a sequence of multi-view images of the same scene. The extracted 2D features are aggregated using a differentiable renderer, namely Gaussian splitting, to generate a sparse 3D point cloud of feature Gaussians, denoted by G. These Gaussians serve as the scene's compact feature representation in 3D space. An important component is the lightweight decoder that converts each low-dimensional Gaussian feature into the full-dimensional space needed to match the original 2D features. The use of low-dimensional embeddings ensure that the storage is efficient and the decoding allows for flexibility in reconstruction. Now transitioning to the right-hand panel, stage 2, 3D-aware fine-tuning, which is multi-scene. Here, we operate at a dataset level, spanning multiple scenes. For each scene, the Gaussian features are rendered into various synthetic views. These rendered feature maps are used to fine-tune a shared 2D backbone model. In essence, the fine-tuning stage acts as a knowledge transfer loop. From each scene, the 2D model learns how feature transforms under different views, leading to a model that better understands 3D spatial relationships, even though it only possesses 2D inputs during inference. One notable aspect of this method is its generalizability. The authors demonstrate that it works across different vision backbones, CLIP, MAE, DATE3, and consistently improves performance in tasks like semantic segmentation, depth estimation, and even generalizes to datasets that are entirely different from the training domain, such as KITTI or ADE20K. Finally, the approach is also computationally elegant. It requires 230 scenes and 8.5 hours of training on a Tesla A100 GPU. This makes it highly practical for academic and industrial use alike. In conclusion, this two-stage pipeline fundamentally enhances the 3D understanding of 2D vision models by embedding them with 3D prior learned via Gaussian-based volumetric rendering. It is a minimal cost, high impact innovation with broad applicability across a range of vision tasks. On this slide, we delve into the feature Gaussian, the fundamental building block of our 3D scene representation. Each feature Gaussian is an oriented ellipsoid in 3D space characterized by mean, mu, the 3D center of the Gaussian, covariance encoding its spatial extent and orientation, opacity, controlling volumetric density, feature vector f, a low dimensional embedding that is 32 or 64 degree dimensional. As such, optional spherical harmonics for U-dependent color behavior. These Gaussian together form a sparse yet expressive cloud that captures both geometry and learned semantics. We start with dual branch rasterization. We render the Gaussian cloud into two parallel rasterization pipelines, each enforcing a distinct supervisory signal. First is color rasterization. We perform differentiable volumetric compositioning, accumulating opacity, weighted colors along each camera vary through the Gaussians. The objective is to match these rendered RGB images to the ground truth photographs. The loss LC of a photometric penalty, commonly L1 or robust L2, between the rendered pixel RGB and the real image I1. This ensures our Gaussians reproduce accurate lighting, shading, and appearance. Second is feature rasterization. The process includes, instead of colors, we blend each Gaussian's latent vectors f along rays to produce a low-dimensional feature map f-low. The decoder, a compact CNN, up projects f-low into a high-dimensional feature prediction f-high, mirroring the output space of our 2D backbone. Think of this decoder as a key to the bottleneck plus expansion steps in modern super resolution or autoencoder architectures. The purpose of this branch forces Gaussians to encode not just color but also semantic and geometric feature structures. By coupling these two strategies, we jointly learn Gaussians that are photometrically faithful and feature consistent across views. Supervising the 2D backbone. The ultimate goal is to inject 3D awareness back into a standard 2D vision model, denoted by epsilon 2D. For a real image, II, we run epsilon 2D to obtain its feature map, Fi. We compute the feature consistency loss, LF, LF, which is the difference of Fi and Fi, where D is a distance metric such as cosine similarity or L2, whichever you want to use. Minimizing LF encourages the 2D model to align its single view features with the multi-view informed features produced by our Gaussian model. This process effectively distills 3D structural priors into the 2D backbone, so that at inference time, when only a single image is available, the network retains a richer understanding of depth, occlusions, and spatial consistency. Coming on to joint optimization objective. All Gaussian parameters, mu, sigma, alpha, f, sh, are optimized simultaneously over n views by minimizing gcap, which is argmin of photometric and feature consistency equations. The tight coupling guarantees that each Gaussian must simultaneously explain the scene's appearance and backbone's semantic embeddings. The result is a compact 3D representation that fully encodes the information needed to supervise our 2D model. Some of the real-world context of this feature Gaussian applications are AR systems, where modern AR frameworks reconstruct basic geometry from RGB input. Adding feature Gaussians could embed object semantics directly into the scenes for more intelligent occlusions and interactions. Another one is photogrammetry, where traditional photogrammetry uses mesh reconstructions. Our method complements it by encoding material and semantic labels. These second real-world parallels highlight the practical impact of embedding learned features into 3D, while the core methodology remains a unified, mathematically grounded framework for 3D-aware feature learning.
So now let's begin with a look at the proposed algorithm and how it integrates 3D reasoning into 2D vision models. The first step is pre-training per scene 3D Gaussians. Essentially, for every training scene, they construct a 3D Gaussian representation using multi-view images. This stage is critical. It captures both geometry and the appearance of the scene in a compact and differentiable form. You can think of this as a building a soft, spatially aware representation of the scene that can be rendered from any viewpoint. Next, they initialize a 2D vision model with a pre-trained feature extractor, most commonly something like Dino V2, which already encodes rich semantic information from large-scale image data. This gives them a strong baseline before introducing any 3D inductive bias. The core of this method lies in a novel fine tuning loop, which works as follows. First, they sample a random scene and camera viewpoint. This ensures that the model gets diverse supervision and sees the scene from multiple perspectives. Then, from that viewpoint, they render a 3D aware feature map using Gaussian representation. This rendered map preserves 3D context and acts as a soft projection into 2D space. Then they extract features from the same image using the 2D model and compare them with the rendered 3D aware features using a loss function, typically L2 loss function. And finally, they update the 2D model's parameters via backpropagation. so that its features become aligned with the 3D aware representation. So the remarkable thing is the efficiency of of this process. Unlike traditional 3D to 2D transfer learning methods, which can be computationally intensive, this method only requires a few epochs to converge. In fact, the authors report that even a single epoch of fine tuning, which takes around 8 to 10 hours, is sufficient to obtain majority of the performance improvements. After this fine tuning phase, the model is frozen and then they train simple linear classifiers or linear probes on top of the features for downstream tasks like semantic segmentation and depth estimation. So now let's check the results and evaluate how well this method performs in practice. We'll start with within domain performance, meaning datasets that share characteristics with the training data. This includes ScanNet++, NYU V2, and ScanNet, which are common benchmarks for indoor scene understanding. On these datasets, the method showed notable improvements. For semantic segmentation, it achieved an increase of up to 2.6% in MIOU, which is quite significant given the maturity of these benchmarks. In terms of depth estimation, the model consistently reduced RMSE, leading to more accurate and reliable depth predictions. What's even more impressive is the performance in the out of domain datasets. These are the datasets that differ significantly from the training distribution. The authors tested the model on ADE20K, Pascal VOC, and Kitty dataset. Despite the domain shift, the model maintained strong performance, indicating that it had learned generalizable features rather than overfitting to specific datasets. Another important aspect of the evaluation is the architectural generalization. The authors didn't limit their method to one backbone. They also tested it on models like CLIP, MAE, and D3. Across all these architectures, the method led to consistent improvements. This proves that the approach is model agnostic and can be applied to a wide range of vision transformers. So, in conclusion, this work introduces a novel and effective way to imbue 2D vision models with 3D spatial awareness. The key idea is simple yet powerful. Leverage pre-trained 3D Gaussian representations to guide the 2D models during fine-tuning. This alignment allows the 2D model to inherit a form of 3D understanding without explicitly predicting the depth or geometry during inference. The approach stands out for three main reasons. First, it is efficient, requiring minimal training time to deliver strong performances. It is architecture agnostic, meaning it can be plugged into various transformer based models without the need for architectural changes. And third, it is generalizable, effective not just on the training domain but across diverse datasets and tasks, even those that are out of domain. So, overall, the results suggest a promising direction for the future research in vision. Rather than treating 2D and 3D as separate modalities, we can unify them through intelligent feature alignment. This could unlock more robust and versatile models for real world perception tasks. So, thank you for listening.